or independent events. We're going to take a look at what we mean by that and how to find them. So first of all, let's take a look at the independent events, the definition. So independent events are events that do not affect the probability of each other. And of course, that doesn't mean that they can't happen at the same time. They can, of course, happen at the same time, just that that one event happening doesn't necessarily change the probability of the other event happening. So dependent events in converse, of course, are events that specifically have a different probability for the second event. So that's given that the first event that has happened, it affects the second event. Okay. So ways that we can figure this out is if we find that the intersection of the two events is simply multiplying the two probabilities together like we would expect, right? Then we know that the events are independent. However, if we find that the intersection of the events happening, that those two events can both happen, right? Events A and B happen, is equal to the product of the event A and event B only given A has happened, right? Then we find that we're looking at dependent events. So perfect examples here are looking at decks of cards and whether or not we replace the card, okay? So if you choose a card from a deck of cards, of course the probability of choosing any given card is 1 in 52, but if you leave that card out and choose a second one, right, and create a conditional probability right there, create a condition to it, then your probability reduces to 1 out of 51. So the idea here being is that the probability of choosing a 5 and a 6, right, in this situation here where we have replaced the card is equal to choosing the 5, which is 1 out of 52, times the probability of choosing a 6, which is also 1 out of 52. And of course, I'm not going to go into what that is. You can calculate that for yourself if you like. It doesn't affect how this works. Okay. The idea here being is that our second factor in this product here is the probability of choosing a 6. It is not the probability of choosing a 6 given you've already chosen a 5, right? It is still 1 out of 52. In contrast, the idea next is that if we do not replace the card, the second one's going to change. So the probability now of choosing a 5 and a 6 from a deck of 52 cards is, of course, the probability of choosing a 5, which is 1 out of 52. But now that we've pulled out the 5 and we have not replaced it, we're multiplying that times a different number. We're multiplying that times 1 out of 51 because we now only have 51 cards in the deck. So choosing a 5 and choosing a card, it doesn't matter what it is, but choosing any card and not replacing it has affected the probability now of choosing a 6. So the probability of choosing a 6 given you've already chosen a 5 is 1 out of 51. And these are not actually true because, well, it's one card, yes, so it's one card, so it's fine. Probability of choosing a 5, of course, is not 1 out of 52. It's actually 4 out of 52. We could change all of those. It's early this morning because, well, we're dealing with cards here. So 4 out of 52. In this case here, again, the rest hasn't changed. It's not 1 out of 52. It's 4 out of 52 and 4 out of 51. Our denominator doesn't change because we're not choosing a 5. Of course, the second one, if we said the probability of choosing a 5, given we've already chosen a 5, would be 3 out of 51. That hopefully illustrates that point. Let's apply that to a few situations. Okay, so what we need to determine here is we need to essentially we need to multiply these two together and find are they equal to the probability of A and B. So the probability of A and B is equal to 27 out of 200, 27 200ths. Okay, we're going to look at, first of all, the probability of A times the probability of B. Okay, so probability of A times the probability of B is 9/20ths times 1/4. So that, of course, is 9/80ths. Okay, and are these equivalent fractions? Well, if we multiplied times 3 above and below, which is what we get for 27, so times 3 above and below, we'd find that we get is equal to 27 240ths. So these two are not equal. So these two are not equal, right? And therefore, these two events are dependent on one another. They're not independent, right? And of course, if you then took, okay, well, so what I'm going to do now is I'm going to say, well, if you can find the probability of B given A, then you can figure that out. So we're just looking right now at the probability of A times the probability of B, and if they are equal, we know that they're independent events. Otherwise, they're not. Okay. So a second example here: the probability of A given B in this second example is 91 200ths. Right, and we've got the probability of A and the probability of B here. Okay, so we're looking at 13/20ths times 7/10ths. Okay, so we're looking at here is 91. 13 times 7 is 91, and 20 times 10 is 200. And as you can see, those two are equal. And so these two, this one here, these events, so A and B are dependent events. Or another way of saying they're not independent. Of course, in this case here, A and B are independent events. Now, it's worthwhile noting here, just on a side note, that, and I'm not sure if we cover it in this course, but on a side note, that independent does not mean mutually exclusive. Okay, so just be aware of that. They're two different things. For mutually exclusive, we use the addition rule. For independent, we use the multiplication rule. In some situations, you might find that they provide the same result, and therefore are both mutually exclusive and independent, but we're not dealing with that in this particular course. Right. So there's our refresher right there, that independent events do not affect the probability of each other. There's your formula. It's a multiplication. And dependent events have a different probability, and that's that condition that's showing up here. And of course, that condition can be written backwards as well. You can say is equal to the probability of B times the probability of A given B, right? So long as you flip everything. Okay, that's also true. Okay. So here's an example. Here, a coin is tossed in a single. And a single six-sided die is rolled. So two different things happening. We'll find the probability of landing on the head side of a coin and rolling a 3 on the die. Okay, so the probability of landing on the head side of the coin is 1 over 2, and so we're looking first of all the probability of heads and rolling a 3 and 3. Is equal to half, that's the heads, so that's the probability of heads, and probability of rolling a 3 is 1 out of 6, which is of course equal to 1 out of 12. Okay, what you notice here is that the 3 is not dependent at all on rolling aheads, so these are independent events. And of course, you're being asked to, first of all, determine if they're independent, then find the probability of events. So we'll do that with the second one. So a class consists of 9 boys and 11 girls. A group of 3 is picked to give a speech. Find the probability that they will all be girls, that they all will be girls. Okay, so what we're doing here is we've got a group of 3 being picked to give a speech. So presumably you're picking one and then picking another and then picking another. So what you have here, so it's the probability that they will all be girls. So the probability that you get 3 girls in a row, so the probability of girl, 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 right? 3 girls in a row, and think about this. This is the same as the probability of getting a girl first time, right? And then times the probability of getting a girl the second time, given you've also already given, so maybe we should say girl 1. So probability of getting girl 2 given girl 1 times the probability of getting girl 3 given girl 1 and girl 2. So notice here that we're already showing a lot of conditionals in here. There's conditions on it, and therefore these events are dependent. Okay, so finding the probability is not as difficult as you might assume. So probability of choosing a girl, first of all, is 11 out of 20. Right? Now you've already chosen a girl, so your denominator is going to change to 19. Okay, and you've chosen one of the girls, so that's actually 10 out of 19. Okay, and the third one here, you've now 2 of the girls, you're not replacing them, you've taken them out, so you've got actually 18 in your denominator, and you've taken 2 girls out as well, so you get 9 out of 18. So we can multiply all 3 of these together. We get ourselves 11 times 10 times 9, which is 990. Of course, we could have simplified this ahead of time as well. 20 times 19 times 18 is equal to 6,840. I'm going to just convert this to decimal for you. 990 divided by 6,840 is equal to about 14. So it's roughly about 14.5%, 14.473 and change. Of course, you could have canceled above and below. That's of course a half right here for simplifying. Right, but you can see here these are dependent because there's conditions to it. Okay. All right. So these ones here, we need to actually do the math to figure out this one to see if it's actually if they're independent. So we're just going to take our A and our B, a probability of A times the probability of B, to determine. All right, so 2/5 times 3/10. All right, so that's equal to 6/50, which is equal to 3/25. And so therefore, these events are independent. Right, because they are the same. Okay, so they are the same. So is equal to the probability of A and B. Okay, so hopefully that kind of illustrates that a lot easier. Okay. And let's look at one last example right down here. One last example. Once again, we're going to take the probability of A times the probability of B to determine whether or not these events are independent, and we get ourselves 1/2 times 2/5, which is equal to 2/10, which is equal to 1/5. And of course 1/5 is not equal to 3/20. okay, which is the probability of A intersection B, right? And therefore, these events are dependent on one another. Okay, so that's independent and dependent. Using those, using the multiplication rule, you can determine whether events are dependent on one another or whether they're not dependent on one another. And if you've got any questions, let me know.